Example 5, the population of the world was 6.5 billion in 2005. So we're going to assume t equals 0 correspond to the year 2005. Then we say in that case P, the initial population at that time was 6.5. Remember, this is in billion. And observed relative growth rate, R, is 1.1%. So we know that the population after a given time is 6.5 e to the 0.011 t. That will tell me, where t is in years, starting with 2005 being 0, that will tell me the population of the planet at any given time. Estimate how long would it take the population to double. Well, 6.5 billion times 2 is 13 billion. So how long would it take until the population of this planet become 13 billion? Well, this is an exponential equation. You isolate the exponential by itself. So hopefully this is getting old, meaning you're getting really comfortable with that. 13 divided by 6.5 is 2. That's double. It's not a coincidence that this always happens. Transform to log form. And divide by 0.011. And t will be in how many years, or by what year? Well, you could just say years. That's not a problem. If I take natural log of 2 divided by 0.011, it's going to take 63.013 years. 63.013 years. So roughly in the year 2068, we're going to have roughly 13 billion people on this planet. How long would it take the population to reach 20 billion? Well, 20 equals 6.5 e to the 0.011 t. Isolate the trig function by the exponential function by itself. Divide by 6.5 both sides. And you could simplify this. There's no need. You could just proceed and transform this to log form. Log base e, which is natural log of 20 divided by 6.5, will equal 0.011 t. Divide by 0.011. So again, this hopefully is becoming like second nature because we do this non-stop. We will have 20 billion in natural log of 20 divided by 6.5 divided by 0.01. 102.2 years. 102.2 years, roughly. Here's another problem. Europium deposit in the kidney is assumed to be retained there with a biological half-life of 10 days. So this substance dies, half of it dies every 10 days. So when they give it to you in the kidney, the hope is that it gets out of there as quickly as possible. Suppose 40 milligrams were deposited into a patient's kidney. Find the model. Well, we're going to use A equal, the initial amount is 40, e to the RT. Now they gave me the initial amount, that's very good. I still have to find R, and that's how I'm going to use this information. In half of the 40 will decay, that means 20 will be left in 10 days time. Now I can solve for R. This is an exponential equation. Isolate the exponential equation by itself. Transform to log form. And R will equal natural log of 1 divided by 2 all over 10. So I could leave it like that. I could plug it in my calculator and use answer, whatever you want, and A will equal 40E. And I need to figure out what this R is. Parentheses, natural log of 1/2 or 0.5, whatever you want. 1 divided by 2 or 0.5 divided by 10 is the rate of growth. That is negative, actually it's decay in this case because it's dying, negative 0.069 and few decimals, 3147. 3147. So negative 0.0693147 t. That would be the formula that I will use to figure out anything else. Well, first things first. How much of the sample will be retained after 25 days? A will be 40. E to the negative 0.0693147 times 25. The amount of milligrams remaining in the system. And they do this to test certain things in the kidney. 40 E. Remember, my answer still holds that value I just did, times 25, 7.07. 7.07 milligrams. How many days will it take for the kidney to retain 1 milligram? 1 equal 40 e to the negative 0.0693147 times t. Well, isolate the trig function by itself, divide by 40 both sides, transform to log form. There's a 1 in there. I forgot about the 1. So divide by negative 0.0693147. And the number, remember t is in days in this case, would be, and now again it's a calculator problem, I will take the natural log of 1 divided by 40 close parentheses divided by a negative 0.069347. Now, that will take 53.2 days. 53.2 days. So, a little less than 2 months that will get out of the kidney. Radium-221 has a half-life of 30 seconds. How long would it take 90% of the sample, or a sample, to decay, I should say? Anytime they don't give us an initial amount, there are 2 ways of doing it. I'm going to go by the simple way. If they don't give us an initial amount, let P equal 100 grams, milligrams, liters, milliliters, whatever it is. So, radium has a half-life of 30 seconds. If I start with 100, in 30-second time, if I leave this in seconds, that's very good. I could use 30. You want to keep it to minutes, you're going to put half a minute, and now T will be in minutes. That 100 half-life will become 50. 1/2 will equal e to the r times 30. Natural log of 1/2 equal r times 30. So I could say that r is natural log of 1/2 divided by 30. R would be natural log of 1/2 divided by 30. That would be negative 0.0231049. 1049. So, now I have A equal P e to the negative 0.0231049 t. I still don't know what the initial amount is, but then this is what they're saying. As much as you have, how long would it take for 90% of a sample to decay? So again, I start with 100. I'm looking for time. 90% decay. If 90% decay, that means I have, if this is milligrams or milliliters, how long would it take to have 10 left? It's an exponential equation. Anytime they don't give me an initial amount, I could use 100. And 100 is easier than other numbers because it stands for 100%, especially if they're going to ask for a percentage. Isolate the trig function by the exponential by itself. 1 over 10 equal e to the negative 0.0231049 t. natural log of 1 over 10 equal negative 0.0231049t, and t would be natural log of 1 divided by 10 over negative 0.0231049. And for this radium-221, for any substance present, it would take, remember, that denominator is still in my calculator, it's under answer, as you see. So if I take natural log of 1 divided by 10 divided by the answer, it'll take 99.66 days, or 99.7, I'm sorry, seconds, for 90% of that to decay. So this is something that you could use, but it's gonna die out very quickly. The burial close of an Egyptian mummy is estimated to contain 52% of the carbon-14 contained originally. They use this carbon dating for most of these objects. How long ago is the mummy buried? Well, they didn't tell us the initial amount, but they say the half-life of carbon-14 is 5,730 years. So, if I was to assume that 100 is present in t equals 0, in 5,730 years, I'll have 50 left. I'll use that. I'll say, if I had 100 initially, e to the r, in 5,730 years, I will have 50. So 1/2, if you divide by 100 both sides, transform to log from exponential, divide by 5,730, and you notice we're doing the same thing over and over. So r equals, and if I get my calculator out, I'll take natural log of 1/2 divided by 5,730. It's negative 0.000120968. I'd rather you use answer, because if you copied this wrong, you're going to mess up the whole problem. So A equal P e to the negative 0.000120968t. That will find me anything that I need. And now they say, well, it contains 52%. If I started with 100, that's why I like 100, then 52 remains. E to the negative 0.000120968t. Isolate the trig function by itself, the exponential by itself, and you get 0.52 equal e to the negative 0.000120968t. Transform to log form. And divide by the negative 0.000120968. Again, it's a big number. If you don't carry that many decimals, you will be off by many years. And t will equal, how old is it? Well, it should be less than 5,730 years, because in 5,730 years, 50% will decay. Here, only 48% decayed, but I still have that stored in my answer. All what I have to do is take natural log of 0.52 divided by answer, 5,405 years, 5,405 years. Now you'll notice on something like this, they wouldn't write the 0.7 or 0.8 in the book. Most likely they will say 5405 years or 06, because they say if you're counting 5,400 years, 0.2 or 0.8 of a year is irrelevant. It doesn't matter. Just write down what you get and we're both very happy. Last problem. radioactive okay. Radioactivity from Chernobyl. That's the explosion that happened in Russia in 1986, right? The explosion, Ukraine. In 1986, they had a nuclear explosion. The radioactive material in the atmosphere from the nuclear planet, right? At Chernobyl in 1986, it really contaminated the hay in Austria by iodine 131. Now, the half-life for iodine 131 is 8 days. Now, they figured it is safe to feed the hay to the cows when 10% of the iodine remains. How long did the farmers need to wait to use this hay and feed their cattle? Well, A equal PE to the RT. Assume 100 is present. Not 1,000, 100 E to the R in 8-day time. Half of the 100 is going to decay. It's going to become 50. So isolate that exponential function by itself, divide by 100 both sides. 1/2 will be e to the 8r. Transform to log form. And r will be natural log of 1/2 divided by 8, or r will be natural log of 1/2 divided by 8. That will be negative 0.866 434. So, out of this, I get A equal whatever is present, e to the negative 0.0866434t. Now, for them in Austria to be able to use this hay, they need 10%. So if you have originally 100, you need to know how long does it take the 100 to become 10. You could use any number. I use 100 because it's 100%. Divide by 100 both sides, and you will get the 10%. Transform to log form. Divide both sides by the negative. And it will take that many days they have to wait. Otherwise, they will really kill the cattle if they use that hay and it's contaminated. Remember, that number is still in my calculator. So if I take natural log of 1 divided by 10, or 0.1 for 10%, divided by that answer, they have to wait 26.57. So I would rather have them wait 27 days to be safe than sorry. And that's pretty much it for this section.